Hello everyone, and welcome to the second part of my Act to Learn series, where I choose random tech-oriented topics, set myself on a timer, and dive right into them. The results are presented in this video. Thanks for watching and have a good one. Now, I want to start off by saying that this adventure escalated quite a bit considering, well, basically everything. Time, workload, challenges, complexity, and not least, lines of code. What had once started as a 32-hour ticket has now evolved into roughly 28 workdays, which sums up to about 224 hours to date. Yet, I'm still not even finished. But in hindsight, I'm glad it escalated the way it did, since I'm quite satisfied with the results I have up until now. Let me assure you though, having the idea of writing your own password manager can be a quite frustrating one. I started off by researching and seeked out to any help I could find in the tech community. This was quite frustrating since basically everyone advised me to not dive into the cybersecurity and cryptographic scene. There are plenty of professionals which offer good password managers anyway. So, I was up for a thrilling start. Since I couldn't find any videos on developing password managers either, I decided to jump straight into the project. Anything else would just drag me down anyways. Being the .NET developer I am, I chose Visual Studio as my framework and created a new WPF.NET Core project. I set up Git, integrated some more frameworks such as Prism for better MVVM usability, and started off with the most important question at hand. How do I safely store passwords on the hard drive? Typically, you would hash a password whenever you store it. Since you need to retrieve the passwords again after having them encrypted, hashing would not work. The Advanced Encryption Standard, short AES, a symmetrical encryption algorithm used amongst other things by the NSA, is pretty much the best you can go with. Now, since this is a password manager, I decided to go with the 256 bits key size option, the highest security rate. Don't worry though, if you find your program or website to be using the 128-bit version only, that's fine as well. Oh, and just a quick disclaimer. I will not be talking about any detailed AES implementations in this video. There are many things to consider when using this algorithm, for example which block mode to use and how to generate initialization vectors. That may be the topic of a different video, but not for now. Okay, back on track. Like in most other password managers, the 256-bit key would be represented by the master key, which the user had to create upon starting the program. This master key is then used to encrypt all other passwords safely. So one key to rule them all, I guess. If you lose your master key, you're pretty much screwed and could end up like this fellow here. Your encrypted passwords would also be lost. On the other hand, if you do not forget your master key, this is a pretty good way of encrypting data safely and retrieving them whenever you need. All you'd need is that one password. Now, since I wanted this to be working 100% offline while still being flexible and individually controllable, I decided to go with a XML database. That way I could also precisely control what needs to be encrypted and what not. Since a 256-bit encryption cipher can be quite heavy on the resources sometimes, especially if the data piles up, I only wanted to encrypt the data that had to be encrypted, which means the passwords only. Any other entities and models that did not contain any sensible data could just be saved as plain text. As a consequence, I came up with the following database structure. I created a folder which acts as my database. For each record that will be stored in this database, a subfolder containing the name of the entity type will be created. In these subfolders, the actual XML files of the serialized models will be written. After everything has been stored, the database folder will be compromised and zipped. The zipped database is then encrypted using the AES cipher. For that, the 256-bit key is needed, which consists of the user's derived master key, meaning the user inputs a password as a string. This string is then being hashed using a randomly generated salt. A salt is basically a sequence of rubbish characters, which only exists to randomize the hashing process of the password string. It's important to understand that in order to recreate the proper hash of the password again, the salt is needed. Otherwise the hash will be different and there's no way of checking whether the input password is correct. After having successfully hashed the password into a 256-bit key, this hash is then used to actually encrypt the database. Note, the plain password text is not the key for the decryption process. It's the combination of the raw password, the salt, and the hashing algorithm. This makes it practically impossible to brute force and hack the database. To continue, the encrypted file will then be placed into a folder. The salt that was used to encrypt the database will also be placed next to it. Note, this is not a security hole. The salt itself is useless, and the password itself is also useless. The actual master key is never stored anywhere. The salt could later be used as a security certificate if a double authentication is demanded. As the last step, the folder containing the encrypted file and the salt is zipped again. This file then contains all the data that is needed for the user to use the password manager. As I finished up implementing this logic, which by the way took me quite some time, I was faced with the question of how will the password manager look? You see, when you have to start developing the UI, it helps having a clear style or vision in your head. I downloaded and inspected the other password managers, such as Dashlane, KeePass, 1Password and so on. To be honest, I find them to be quite boring. Not in terms of actual UI implementation, but in general style and theme. Simply because there was none. Then something struck me. Anyone that has played Dark Souls will know of the infamous Sense Fortress. A place full of traps, dangerous creatures and obstacles, all with the goal of not letting anyone enter the fortress. The idea of keeping your password safe in a storage chamber deep down in the depth of a fortress dungeon filled with guards and protection services felt very exciting to me. With the user's master key, the gates of his own fortress could be opened. The guards could provide maximum security and retrieve the passwords from the actual storage chamber if needed. With this in mind, it only came naturally to me that the name of this password manager would be Sense Fortress. As I've now decided what style I'll go for, it was time to create the initial UI containing a start screen, a login screen, a register screen, and a home screen, which is opened once the user has logged in. For this, I decided to use the Material Design pattern, which came with some nice transition effects and overall very modern look. For anyone wondering, Material Design is basically used in every mobile app, including the Android operating system. As I've gotten the aforementioned views working out nicely, I now had the basic database access layer combined with the first UI version of the app. It was now time to actually implement some features. The first thing I tackled was the structure in which passwords could be added, the storage chamber. I decided to make it as free for the user as possible, which resulted in creating a tree structure in which the user could add either a folder or subfolder or an actual password entry. While it's possible to place folders under a folder, it's not possible to add a folder under a password. It's the typical root, branch and leaf structure. The topmost folders are the roots, followed by branches, which eventually result in leaves, represented by passwords. As I was implementing the loading and storing of the entities used in the tree view, I suddenly realized I had not yet thought about how to handle passwords in RAM. You see, when the master key is used for decrypting the database, the master key is immediately disposed from the memory. Logically, if you decrypt data, it is then loaded into the memory where the passwords are stored basically in plain text. It is rather unlikely for malicious services to attack the RAM, but a simple memory dump at the wrong time could potentially contain the sensible password data. Also, while the program is running, I needed to have the passwords ready at all time for the user to obtain. If I would not keep them in RAM, I had to decrypt the database each time the user wants to read his password. However, the master key is needed for that. Obviously, no one wants to enter his or her master key each time a single password is read, edited or added. Keeping the master key in RAM at all time is not an option either. If I stored the plain text of the master key in RAM, an attacker could find out the actual raw password. Many users use the same password more than once, so having a raw password of that importance opened up many more doors for an attacker. On the other hand, if I stored the derived master key in RAM, an attacker would have the actual 256-bit key that is required to decrypt the database. No salt needed. It's a lose-lose situation. So I decided to somehow safely store the passwords in RAM after the decryption of the database, so that the master key is never stored anywhere, neither hard drive nor RAM. The first thought that came to my mind was using the secure string class Microsoft had to offer, but I later realized that a secure string is not really as secure as it sounds. A secure string is basically a read-only field that is being kept in memory. If you modify a secure string, a new instance of it will be instantiated by the COM runtime language instead, which then represents the edited secure string. As a result, you now have two instances of a secure string in the RAM, which is definitely not a behavior I want for my purpose. Secondly, a secure string is not automatically collected by the garbage collector. As a result, it's possible that the secure string instance is still kept in RAM even after you've closed the application it was used in. Again, a behavior that is not suited for my case. And lastly, a secure string can still be recognized in RAM dumps, which then offers the ability to reverse the action from secure string back to a normal string. It became clear that I needed something stronger if I wanted to store passwords in RAM for a longer period of time. Luckily, Microsoft DP-API offers an alternative, Crypt Protect Memory and Protected Memory, which encrypts the byte it's given. With DP-API, the key for the memory encryption is stored in a secure, non-swappable memory area managed by Windows. It's important to understand that this key is derived with the current Windows user. If I were to decrypt an encrypted memory snapshot of a different account or PC, the decryption process would not work. So remember, when using Windows DP-API, always make sure that you never accidentally store the encrypted bytes on the hard drive, because the files would then be bound to the user/PC, which can lead to many problems. Anyways, using the Windows DP-API, I came up with the idea of a secure data cache and an unsecured data cache, which both exists in RAM only. The secure data cache would contain any sensible data that should be kept encryptedly. Whenever a password is created or loaded, two models are being created. One that holds the actual raw password, and the other one containing metadata, such as name of the password, created date, and so on. The model that contains the raw password has a foreign key property which contains the idea of the metadata model. It is then put into the secure data cache dictionary/hashmap, the key being the foreign key property of the model, and the actual password is kept encryptedly as the value of the dictionary/hashmap. The other model, which contains the metadata, is put into the unsecured data cache. If a user wanted to retrieve a password, the metadata model is loaded from the unsecured data cache. If the user wanted to see the actual password, the encrypted bytes are fetched from the secure data cache by the ID of the metadata model, and finally decrypted and shown in the UI. With this running and working, I now had a good system for storing data safely on a hard drive and in the memory. The tree structure was working fine as well, which made the password manager usable for the first time. As I've already mentioned, in contrast to other password managers I have looked into, I did not want to store the master key anywhere, not even in memory. After the initial login, it was flushed out of memory for good. One problem that had occurred because of this logic was the actual saving process. You see, no changes made to your Fortress would be saved automatically. Instead, you have to explicitly press the save button in order to save changes, which is a behavior I personally definitely appreciate. Imagine someone gaining access to your computer via a backdoor and remote desktop connection. He would not only be able to steal your passwords if the password manager was running, but he could also modify your data through the program. Imagine you having a 32 characters long password generated for Amazon, and then someone first steals it and then changes it. Without backups, the password would basically be lost. So I had one more scenario to face, which resulted in two problems. An attacker gaining control over your PC, giving him the opportunity to first steal your password and then changing them through the program. As a safety measure for the second case, I made it so no changes could be saved without the actual master key being entered. You have to explicitly press the save button, which then requires the master key to work. To not lose track of the changes you made, I implemented a little changes counter and some UI elements which show what items had been modified. I also implemented a small log which the user could consult if he wanted to explicitly see the changes that were made. As a counter for the first problem, I implemented the ability to lock the Fortress. If the Fortress was locked, it was not possible to change or read any passwords. As I've later implemented more features in Windows, for example a quick bar where you could drag in the passwords you used the most, the user could configure what features he wanted to be disabled upon locking the Fortress. As you can imagine, you can only unlock the Fortress using the master key, which then again unlocked all the features that had been disabled. I was very satisfied with this logic, and as the core functions were now more or less running smoothly, I could now go on to make some usability features. As briefly mentioned before and seen in the background, I started with adding a quick bar to your home hub where you could drag in the passwords you needed the most. I also added the ability to deposit URLs and usernames together with your password as well as a small description. I've then continued to implement the emergency sheet function, which made it possible to print out all the passwords you had stored into the Fortress in case of complete shutdown, and followed it up with some more password safety functions, such as a random strong password generator, and a password analysis tool, which calculates the strength level of a password through some predefined properties, such as password length, uppercase levels, and so on. The user was then informed about the password strength level through UI and more in depth through a pop-up window, which gave a more detailed description of the problems the password had. Lastly, I wanted to add the option of adding custom configurations to your Fortress. For example, what will be disabled if the Fortress was locked, and I also wanted to add the option of automatically backing up and scanning the Fortress in a chosen time interval. For this, I had the idea of a guardian that would constantly patrol in the Fortress and who made sure that everything is safe and all the tasks would be executed. I implemented him by devoting a thread only for him, which was running as long as the user did not stop him through a button in the Home Hub. I then added the ability to set up the backup and scan interval in the settings and let the Guardian handle these custom settings. After this was working fine, I added a Guardian log into the security management window, where the Guardian would report to. These reports include execution of a task, discovering malicious actions, and finding errors in the Fortress or Guardian setup itself. Scanning the Fortress for malicious actions was done by constantly hashing crucial elements of the Fortress, such as the storage chamber, and comparing them with each other. If there were any differences that had not been reported to the Guardian beforehand, something from the outer walls of the Guardian must have changed this data. Let me give you an example. When opening the Fortress by decrypting the storage chamber, a hash of the file is generated and stored in RAM. If the Fortress is being modified by the program itself, for example when saving, the hash of this file changes. This new hash is reported to the Guardian so that he knows that this data had been rightfully changed by the Fortress itself. The Guardian has its own dictionary of hashes for each crucial section of the Fortress. If the Fortress is being scanned, the Guardian checks on these hashes, meaning he takes a hash of the storage chamber himself and compares this hash with the one in his dictionary. If they are not the same, something must have modified the data without the Guardian being informed about it, which ultimately means that the modification was not done through the Fortress, but from somewhere else. In this case, malicious actions were found, and the Guardian immediately reports to the user that something is wrong. Also, every data stream that is being read into the Fortress, for example the configuration file, is checked by the Guardian for its template. If someone wanted to inject malicious code through a file that is being read into the Fortress, similar to an SQL injection, the template of the file will differ from the one that the Guardian knows, which again leads to the Guardian reporting an issue. For the future, I want to expand these scans more and generally add more features, but for now, that's enough. As I conclude this presentation, I wanted to mention that in a video like this, everything comes off easier and more fluent as it actually was. Trust me when I tell you that I did not code my way through these implementations like a hot knife through butter. I redesigned the whole UI probably 10 times, had to change my encryption and safety functions at least the same amount of times, and generally produced more bugs than you could imagine. Most I could fix, some I still don't understand, and the majority I haven't even seen to this very day. Keep in mind that all this took me about 20 tickets, 28 workdays or 224 hours and 5 months to redevelop. Just remember that the next time you feel like you're not moving forward. I also want to mention that I'm not a cybersecurity expert. I am working as a software engineer developer, and all the knowledge I've gathered throughout this project was by self-learning. I would appreciate any feedback to things I've done wrong or completely missed. Finally, if you want to have a look into the password manager yourself, maybe you want to develop something similar or simply use it, feel free to visit my GitHub page. I do plan on constantly working on this project until I feel like it's fully finished. Until then, I hope you liked this video. If you have any questions, just ask them in the comments, and I see you next time on Act to Learn.